So this is part 3 of the chapter 8 lecture videos. At the end of part 2, we talked through the rules on how to draw a Lewis structure. So we're going to go through those rules again and then practice drawing Lewis structures. That's pretty much what part 3 is about. We're going to be drawing Lewis structures. And then at the end, we're going to learn how to know if there's more than one option, which one is the best. So first of all, Lewis structures, their purpose, it's to show us how the atoms in a molecule are actually connected. So when we write their chemical formula, so like CCl4, that tells us how many carbons and how many chlorines, but it doesn't tell them how they're attached. So the point of Lewis structures is for us to show how the atoms are attached to each other, what the electrons are doing. And so Lewis structures are for covalent bonds. So just a quick reminder, straight lines, oops, no, come back. A line represents a bond. And so it's bonding electrons, and each line is 2 electrons. So these are bonding electrons. We're going to see dots. Dots represent non-bonding electrons, which are sometimes called lone pairs because they're not being shared. And each dot represents 1 electron. So those 2 dots are 2 electrons. So we could look at a Lewis structure and count how many bonding electrons there are based on how many lines there are, and we count the number of lines and multiply it by 2. And we could count the number of non-bonding electrons by counting the number of dots. Okay, so each dot represents 1 electron. Our non-bonding electrons, our lone pair electrons, are always going to come in sets of 2. That's why they're sometimes called lone pairs, like a pair is a set of 2. Okay, so let's go through the rules, and then we're going to practice drawing Lewis structures. So the first step says to take the molecule that you're asked to draw, so in this case PCl3, and find the sum of all of the valence electrons in all of the atoms. And if we have a charge, we'll have to take that into account. We will practice doing some with a charge, but this first one does not have a charge. So the valence electrons, if you look back in the chapter 8 lecture video part 2, I showed you a shortcut on how to figure out the number of valence electrons in an atom by which column they are on the periodic table. So group 1 has 1 valence electron, group 2 has 2 valence electrons, group 13, which is starting with boron, has 3, group 14, which starts with carbon, has 4, group 15, which starts with nitrogen, has 5, 16 is 6, 17 is 7, and 18 is 8. The only element that doesn't follow that trend is helium, is in group 18, but if we look at helium, it actually only has 2 electrons, so it can't have 8 valence electrons. But otherwise, everything else follows that trend. So that's where phosphorus, when you find it on the periodic table, it's in group 15. So that's why we have a 5 written there. It has 5 valence electrons. I know phosphorus has a number 15 in its box. I don't care the total number of electrons. I care about the valence electrons, which are the electrons in the highest energy level. So they're the ones on the outside. So when that atom interacts with another atom, it's going to be the outside electrons that interact. So for chlorine, we find chlorine on the periodic table. It's in group 17, so it has 7 valence electrons. We multiplied that by 3 because there are 3 chlorines, and altogether we got 26. So this number, which will be the first thing you do with every Lewis structure, is how many electrons you have to use in your Lewis structure. Not about, but exactly that number. Okay, so between lines and dots, we have to make sure we use exactly 26 electrons in this structure. So step number 2, find the central atom. So the central atom is going to be the least electronegative element. So the periodic table, oh my gosh, that one was special. The electronegativity increases as we follow that arrow, except for group 18. So fluorine is the most electronegative element. So what we're looking for is the least electronegative element. So the one like backwards pretty much. So if we look at phosphorus and chlorine on the periodic table, based on that arrow, chlorine is further to the right, so it is more electronegative, making phosphorus less electronegative. You might look at this and say, well, it was PCl3. There's only 1 phosphorus, so obviously phosphorus is in the middle. There are going to be molecules where there's only 1 of every type of element. You still have to know which one goes in the middle. So don't just trust that you'll always be able to figure it out. Sometimes you can't just figure it out. Okay, so we put the least electronegative atom in the center, put the other atoms around it, and connect them with a line. So the central atom to each outside atom. So far in this structure, I've used 3 lines, which is a total of 6 electrons. So that's why down here at the bottom, 26 minus 6, we're just keeping track of how many electrons we have used and how many we have left. So we have 20 electrons left. Step 3, look at our outside atoms and fill their octet. Octet means 8. So make sure the outside atoms have 8 electrons. So chlorine, before we added the dots, this chlorine right here, before we added the dots, only had 2 electrons around it coming from that line. Okay, so to get to 8, we had to add 6. So we're going to do that by adding non-bonding electrons, by adding dots. So if we count, let me erase that. We've used 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons coming from our dots. So that's why we had 20 left minus 18, so we have 2 left. So we fill the outside atoms with non-bonding electrons to get them up to 8. Then we're going to look at our central atom. And if we go back this step, the central atom, phosphorus right here, has 2, 4, 6 electrons around it right now because it has 3 lines touching it, and each line stands for 2 electrons. Every atom needs to have an octet at the end of our Lewis structure. So right now phosphorus has 6, it needs 8. So we have 2 electrons left. So luckily we have 2 electrons left. We need to put 2 electrons on phosphorus. So step number 4 is to fill the octet of the central atom. In this case, we had 2 electrons left over, so we just plopped them on there. We can double check ourselves, count the number of electrons, make sure we used 36 electrons, and that everyone has their octet. The only exception to the octet that we're going to talk about right now is hydrogen. Hydrogen doesn't want 8, hydrogen wants 2. That's because hydrogen is trying to be like its closest noble gas, which is helium, and helium only has 2 electrons. So hydrogen only will have 2 electrons around it. Every other atom, it's your job, as of right now, to make sure all of them have 8 electrons around them. Sometimes we run out of electrons before everyone has their octet. So if we look at this, we followed the first couple of steps. So this has 10 electrons. 1 from hydrogen, 4 for carbon, 5 for nitrogen, so 10 electrons. Carbon is the least electronegative, and hydrogen can never be in the center, so hydrogen can't be in the middle. So carbon's in the center, so I attached hydrogen and nitrogen to it. Started filling the octets, so nitrogen, I gave it 6 dots, so that way it has a total of 8. Hydrogen has 2 electrons around it already, and hydrogen's an exception, it stays with 2. So if we count, 4 electrons coming from the 2 lines, and 6 electrons coming from the dot, that's a total of 10. But the central atom does not yet have its octet. So we cannot use more than 10 electrons. When we added them up, we had to use exactly 10 electrons. So when you run into this situation, and only when you run into this situation, we're going to make multiple bonds. So we're going to take some of the dots on the nitrogen and make nitrogen share them with carbon. So in this case, it's going to take 2 sets of electrons that nitrogen is going to have to share with carbon. So if we count here at the end, this structure, if we count the number of electrons, 2, 2, 4, 6, 8, 10. So we used 10 electrons, which is exactly what we were supposed to use. Let's check each atom. Nitrogen has 2, 4, 6, 8 around it. Good. Carbon has 2, 4, 6, 8 around it. Good. And hydrogen has 2, which is good for hydrogen. So when there's 3 lines like that, that is called a triple bond. Any guesses on when 2 lines? It's a double bond. And if there's just 1 line, that is a single bond. Okay, so those are our rules. So we're gonna try this with some new molecules. So we have 7. We're gonna go through these buddies, drawing them, following the steps, and checking to see how we're doing with this. So CH2Cl2 is our first structure. So this is the list. What I'm gonna do is give us blank slides for me to draw on. So we're just gonna go one by one through this list. So CH2Cl2 is the molecule that we have to draw. Step number 1 is to look at our periodic table, find all of the elements in this molecule, and add the number of valence electrons together. So we find carbon on the periodic table, and it has 4 valence electrons. We find hydrogen on the periodic table, and it has 1. There are 2 of them, though, so I'm going to multiply 1 by 2. There are 2 chlorines. I'm going to multiply 2 by 7, because that's how many valence electrons chlorine has. And when I add this together, I get 20 electrons. So that means in this molecule, when I draw my picture, it has to have exactly 20 electrons at the end. Okay. Step number 2 is to figure out the central atom. which is going to be the least electronegative element, except it can't be hydrogen. So we know for sure it's going to be either carbon or chlorine because it cannot be hydrogen. So we look at carbon and chlorine on the periodic table. Chlorine is the most electronegative, making carbon the least. I'm going to put carbon in the center, and I'm going to attach all of the other atoms to it. It does not matter how you arrange the two hydrogens and the two chlorines. I decided to put the two hydrogens next to each other and the two chlorines next to each other. You could do HCl, HCl. It doesn't matter. Okay, so as long as out on the outside there are two hydrogens and two chlorines, then you've set this up correctly. So far, we've used 8 electrons. So I have 12 electrons left to use. Step 3 tells us to look at our outside atoms and fill their octets. So hydrogen, we do not add more because hydrogen only needs 2 electrons, and that's what it has right now. But chlorine currently has 2 electrons around it. Chlorine needs its octet, which is 8. So I'm going to add 6 electrons around the chlorine to give it a total of 8. And then I'm going to do the same thing for the other chlorine. Now let's count. We've used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 dots. So that's 12 electrons. So we have currently used all 20 electrons. Next step is to look at your central atom, so carbon, and fill its octet. Well, let's look to see how many electrons carbon has. Well, carbon currently has 4 lines around it, where each line represents 2 electrons. So carbon already has its octet. So that's my Lewis structure for carbon. So the things we're checking for at the end to double check that we used the correct number of electrons and that everybody has an octet. Okay, and then just a heads up, in Canvas, right above the videos, so right after the chapter 8 notes file, there is a file that is like Lewis structure something. Let's see what's it called. Never mind, I'm not going to do it right now. Fine. Where'd you go? Nope. I didn't mean to exit the tablet mode. Did I really close it? Of course I did. Well, okay. So the Lewis structure handout, there we go. That's what I'm looking for. I've made that. That has a list of the steps that we just talked through, and then some examples down there. And then there's going to be some more things that we're going to talk about in chapter 8, and that is going to list those as well. Nope, that's not what I want. There we go. Okay, so now we're going to go on to the next molecule. The next molecule on our list is ASO3 with a 3- charge. You don't have to know the name of the thing to draw the Lewis structure, so just so you know that. So step number 1 is to add together the electrons. So AS is arsenic. We find it on the periodic table in group 15, so I'm going to have 5 electrons there. We have 3 oxygens, so it's going to be 3 times the number of electrons for oxygen, which turns out to be 6. Okay. Now, there's a charge. We haven't dealt with the charge before. So it's a 3-. Remember, what we're adding together right now are the number of electrons. If something has a 3- charge, that's telling us it has 3 extra electrons than if it had a 0 charge. So we're going to have to add those in. We're adding together electrons. So I know it's -3 is the charge. But we're adding electrons. -3 represents 3 electrons, so we're adding that together. So when I do all this math, I end up with 26 electrons. Okay. Step number 2 is to find the central atom, which is going to be the least electronegative element. Oxygen, according to the trend, is the most electronegative element between the two. So arsenic is the least, so I'm going to put it in the middle. And then I'm going to attach the oxygens to it. It doesn't matter how you attach the oxygens, as long as the arsenic's in the middle and there are 3 lines branching off of that with O's at the end. I don't care if it's at weird angles or pointing up or down, like whatever. It's just the fact that there's arsenic in the middle, 3 lines coming off of it to 3 separate O atoms. So far we've used 6 electrons, 2, 4, 6 for the 3 lines. Just keeping a running total here. Next is to look at the outside atoms and fulfill their octet. So each oxygen atom currently only has 2 electrons around it. So I'm going to give each of them 6. So that way 2 plus 6 equals 8. That's what we're going for. So now let's count how many dots we just added. So 2, 4, 6, 8, 10, 12, 14, 16, 18. So we have 2 electrons left. Okay, our outside atoms have their octets. So next step is to look at our central atom. Our central atom currently has 6 electrons around it. It needs to have 8. We happen to have 2 electrons left, so I'm going to take those 2 electrons and put them on the arsenic. So now it has a total of 8, so minus 2. So I'm down to 0 electrons, which is what we need to do. We have to use exactly 26 electrons. We've used 26 electrons. Every element has 8 electrons around it, so there's our Lewis structure. Let's try SiH4. And what I would love for you guys to do is whenever you feel comfortable, once I write the formula at the top, you can pause the video and on paper in front of you, try drawing the Lewis structure. And once you're done, listen to the video, because that's what we'd be doing in class right now, is I would be writing them on the board and making you practice them once you felt comfortable. Because with these, you just have to practice drawing them. That's the thing. Okay, so we're going to start by adding together our electrons. Silicon has 4 valence electrons. There are 4 hydrogens, so I'm going to take 4 times the number of valence electrons for hydrogen, which is 1. So my Lewis structure has 8 electrons. I've got to pick my central atom, which is going to be the least electronegative element, and it cannot be hydrogen. So actually this time, I know it has to be silicon. And we're going to attach the hydrogens to it. So we're going to count our electrons, 2, 4, 6, 8. We're at 0 electrons already. Let's check our outside atoms. We're supposed to check for their octet. Well, hydrogen doesn't want an octet. Hydrogen wants 2. All of them have 2. Let's check our central atom. Silicon does need 8 electrons. If we count, it has 8 electrons. Okay. Carbon monoxide is our next one. So let's count together our valence electrons. Carbon has 4 valence electrons. Oxygen has 6 valence electrons, so the whole molecule is going to have 10. Now I know there's only 2 atoms, so we know they're going to be attached to each other, but I still want us to figure out the central atom. So every time, figure out what the central atom is. So the central atom is the least electronegative atom, and carbon is the least electronegative between these two. Oxygen is the most electronegative. So I'm going to write down carbon first, then I'm going to attach it to oxygen. Okay, now we're supposed to fill the octet of our outside atom. So our outside atom is the oxygen because carbon is the central atom. So I'm going to add 1, 2, 3, 4, 5, 6 dots to the oxygen. So it has a total of 8. I guess I haven't been doing a good job of keeping track. So let's count our number of electrons so far. 2, 4, 6, 8. So I have 2 electrons left. The oxygen looks good. Now let's look at this central atom, which is the carbon. And we need to give it an octet. Well, right now it only has 2 electrons. Well, we have 2 electrons left, so I'm going to go ahead and put those electrons on the carbon. Minus 2. So we're at 0 electrons. Well, we are not done, though, because carbon only has 4 electrons around it. 2 dots and 1 line, which add together to equal 4. I cannot just add ... to it because I have to use this number of electrons. So this is when we run into the situation where we're going to have to make the outside atoms share. So I'm going to take the oxygen, and I'm going to take 2 of its electrons, any 2 you feel. I'm going to take 2 of its dots, and what I'm going to do is replace that with a line. So if we count, the oxygen still has 2, 4, 6, 8 electrons around it. ... that's 4, plus 2 lines, 2 electrons each, that's 4, so 4 plus 4 is 8. And now carbon has a total of 6 electrons around it. That's not 8. But it used to have 4, and now it has 6. So now we're going to take another set of electrons of the oxygen. And it doesn't matter which set of 2 dots that you take, and we're going to exchange it for a line. So if we count, oxygen has 2 dots, so 2 electrons, plus 3 lines, which is a total of 6 electrons. 2 plus 6 is 8. Carbon has 2 dots, plus 3 lines, that's 8. If we count the total number of electrons, we have 4 dots in the whole picture, which is 4 electrons. 3 lines, which is 6 electrons, because each line has 2 electrons each. That's a total of 10. So we've used our magic number 10 of electrons that we figured out at the beginning. Each atom has an octet, so this molecule is correctly drawn. This is what carbon monoxide looks like. So carbon monoxide has a triple bond. And notice, I didn't necessarily know that at the beginning. When I started this, I was just plopping along, following my steps, doing what I need to do. So you don't start by trying to put double and triple bonds. Just follow the steps, okay? So next one is nitrate, NO3 minus 1. So let's start by figuring out the number of electrons. So nitrogen has 5 valence electrons. We have 3 oxygen, so it's going to be 3 times 6 valence electrons. And that negative charge, I'm going to have to add 1 extra electron, because that's what the negative is telling us, that we have 1 more than we normally would have. So I get 24 as my total. Now I'm going to give you a heads up. When you add these electrons together, you're always going to get an even number. If you don't get an even number, you did it wrong, 100%. There are molecules that have an odd number of electrons, but you're not going to be drawing them. So if you add up your electrons and you get an odd number, so like if you forgot to take care of that negative and you just did 5 plus 3 times 6, you would get 23 electrons. You'd be like, oh, wait a minute. Okay, because everything we've done comes in sets of 2, right? A line is 2 electrons. When we do dots, I'm putting them in as sets of 2. Okay, so you better have an even number. And if you don't, you know you did something weird. That 3 is really bothering me. Okay, better. All right, so now we need to figure out the central atom, which is the least electronegative atom. So between nitrogen and oxygen, nitrogen is the least. And then I'm going to attach the oxygens to it. So I've used 2, 4, 6 electrons. So now I'm going to look at my outside atoms and fill their octets. So I'm going to add 6 dots to each oxygen, because right now each oxygen just had 2 electrons coming from the line. Now I need to count what that was. So 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, so I used 18 electrons, so I'm at 0 electrons. So I have no more electrons to add to my picture. The outside atoms are happy. Let's look at the central atom. The central atom. How many electrons do you think are around that nitrogen? 6. 2 from each line. 2, 4, 6. 6 is not an octet. Octet means 8. So we're not done with our Lewis structure yet. And I cannot put 2 more dots on there because I'm at 0 electrons. I ran out of electrons. So this is the situation when we have to worry about making multiple bonds. We're going to pick one of the outside atoms. As of right now, pick the one that you like the most. I'm going to pick the one that's pointing down because for some reason that one is the one I like the most right now. And I'm going to take 2 of its dots and turn them into a line. So all we're doing is moving electrons that used to be just on oxygen and making oxygen share those electrons with nitrogen. So I want to count just to make sure that we still have 24 electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Awesome. The oxygens, I want to count to make sure they each have 8. So 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. And the nitrogen currently also has 2, 4, 6, 8 electrons around it. So this is my final Lewis structure. Now, when you were drawing this Lewis structure, when it was in this, well, I don't know why that's floating off over there. Yeah, this doesn't work as well as it does with a whiteboard marker. When it was in this situation and we decided we had to share, if you had chosen like this atom and done that, you're still right. Or if it looked like to put more effort into making my electrons. Oops, stop it. Nope. No. I don't know what I just turned on. Oh, subtitles. Okay, I'm gonna pause and figure out how to undo what I just did. Are the subtitles still there? Yes. Okay. Sorry, I couldn't tell until I hit record if it was working or not. So we're gonna move on to our next one. We have 2 more. I don't know what's beeping at me. 2 more Lewis structures to do, and then we're gonna look at a situation of what happens if you can see there's more than one option and how do you choose that. So ClO2, which is the chlorite polyatomic ion. So first you add together the number of electrons. So chlorine has 7. There's 2 oxygens, so 2 times, and oxygen has 6, and that minus charge is going to be 1. So this is a total of 20 electrons. So in my picture, I've got to have 20 electrons. So now I've got to choose which one is the central atom, and it's going to be the least electronegative. And if we look at this, oxygen and chlorine are tough to tell between because they're both touching fluorine. Like they're both, like chlorine is most to the right, and oxygen is further up. Well, To give you a hint, oxygen is very rarely in the center. The only time it's in the center is pretty much water. So oxygen is going to be an outside atom. So in this case, the other hint is that you only have 1 chlorine and 2 oxygen. So I'm going to put chlorine in the middle, and oxygen and oxygen. Again, it doesn't matter where you put the oxygens as long as they're branching off of the chlorine. So I've used 4 electrons. Now I'm going to look at my outside atoms and give them their octets. So I've used 2, 4, 6, 8, 10, 12. So I have 4 electrons left. Now we're going to look at our central atom and see if it has an octet. Well, right now, chlorine has 4 electrons around it. So to get to 8, it needs 4 more. We happen to have 4 electrons left. So when I have electrons left, I'm just going to place them on the central atom. So now chlorine has 8. Oxygens each have 8. Now let's double check that we used 20. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So that's my Lewis structure. We don't always have to do double and triple bonds. And actually, if you tried to do a double or triple bond in this molecule, you'd be wrong. So there's not like multiple right answers here. There's the right answer, and then there's all the wrong ones. Okay. So last example is carbonate. No. So 4 from carbon, 6 from each oxygen, 2 from the -2 charge. Gets me a total of 24 electrons. Carbon is going to go in the center. I put the oxygens around it. So I've used 6. I'm going to give the outside atoms their octets. Hmm. 2, 4, 6, 8, 10, 12, 14, 16, 18. So I'm at 0 electrons. So I have no more extra electrons I can add. The outside atoms are great. The central atom is what we need to look at next. Carbon currently only has 6 electrons around it. Can we add 2 more dots to it? The answer is no, because I don't have any dots left to add. Again, this is when we have to do the sharing situation, when we've run out of dots. So I'm going to choose that oxygen, because I want to, and take the 2 dots and turn it into a line. So now carbon has 8 electrons around it. The oxygen still has 8 electrons around it, 4 dots and 2 lines. And the other oxygens are great, so that would be my Lewis structure. Okay, awesome. So last thing, and then we're going to practice this last thing on the next slide, but I want to talk about it, let it sink in, is when we do, well, Lewis structures, sometimes it's possible that following those rules, you could come up with a Lewis structure and I could come up with a Lewis structure, and both of our Lewis structures followed those rules. So like, for example, the CO2 down in the little blue boxes, there's 2 different structures of carbon dioxide. Carbon with 2 double bond to each oxygen, carbon with a single bond to one and a triple bond to the other. And if we follow the rules, all of them, both of them, I mean, there's only 2, but both of them have the correct number of electrons. They have 8 electrons around every atom. It follows all the steps. But what I just said when we were just a couple of examples ago, there's 1 right answer and a bunch of wrong answers. Both of these are not correct. One of them is correct and one of them is not. But the issue is right here, you wouldn't know which one was winning or losing based on the rules we've talked about because they both follow the rules. So that's what formal charges are. Formal charges are a way to check how good your Lewis structure is. Number 1, when you draw your Lewis structure, you might not even recognize that there's another option. Like you might have drawn this one because it followed the rules and been like, good job, I met all the requirements, moving on. So starting now, we're going to calculate the formal charge for every atom in every Lewis structure we draw. And I know that sounds tedious, but that's how you know if your structure is good or bad. Okay, so we're going to talk about how to calculate the formal charge, and then we're going to backtrack some of the pictures that we've already drawn and calculate their formal charge. So formal charges in words. For each atom, count the electrons in lone pairs and half the electrons it shares with other atoms. Subtract that from the number of valence electrons in that atom. So that's what this equation is right here. I don't like it. So this is going to be me rewriting it in different words. So FC is going to stand for formal charge. Okay, so how you're going to calculate the formal charge. You're going to take the number of valence electrons of that atom. We're looking at one atom at a time. minus the number of dots on that atom plus the number of lines on that atom. That's how we calculate the formal charge. Okay, dots plus line. So looking at oxygen that I put a little number 1 next to. Its formal charge. Well, oxygen has 6 valence electrons, so 6 minus, it has 4 dots and 2 lines, so I get 0. Carbon has 4 valence electrons, it has 0 dots and 4 lines, so I get 0. And then this oxygen over here is the same. So this one's got a 0, oops, come back, no, a 0, a 0, and a 0. So over here, that oxygen has 6 valence electrons minus 6 dots and 1 line, so I get -1. This carbon has 4 valence electrons minus 0 dots and 4 lines, so I get a 0. And this oxygen is 6 valence electrons minus 2 dots and 3 lines, so I get a +1. Okay, so you can do addition and subtraction. Good job, woohoo. What do these numbers mean? A 0 formal charge is awesome. A 0 formal charge is, it's balanced, it's happy, the arrangement is great. 0 formal charge is good, okay? If you have a formal charge other than 0, we do have there's going to be times where it's not possible to get them to 0. For example, ions, their formal charges are going to add together to equal their total charge. So if something's got a -1 charge, one element's going to be -1. Like, there's nothing we can do about that. But first, we're going to stick with 0 is the best. So if C with the double bonds has a 0, 0, 0, and the carbon dioxide with a single bond and a triple bond has a -1, 0, -1, well, 0, 0, 0 wins because all the atoms are in their best situation, okay? So that's how we can double check. Now, if you had drawn the triple bond, single bond one, and you saw your formal charges are -1, 0, +1, you should be like, stop. That's not good. See, at that point, if there's another way that you can draw the Lewis structure, that's your warning that your Lewis structure doesn't look awesome. So let me erase. We're going to come back, and so the best Lewis structure is the one with the fewest charges, which means most zeros. And if there has to be a formal charge, it has a -1 on the most electronegative atom. So in the examples down below, there's 3 Lewis structures, and on the outside it has a minus charge. What that's telling you is it's an NCO has a -1 charge. So it's impossible to get all of them to have 0 formal charges. So what I'm going to do is let's decide which of these 3 structures is our winner, is our best one. Okay, so just a reminder how we can calculate formal charge. It's the valence electrons minus number of dots plus the number of lines. Okay, so nitrogen, 5 valence electrons minus 6 dots and 1 line minus 2. Ouch, that's bad. So if 0 is the best, having a -1 or a +1 is bad, but like sometimes it might have to happen. If you get down to a -2 or a +2, it's like I would almost stop looking at this molecule and just be like, you suck, buddy, you lose. But I'm going to go ahead and we're going to keep looking at the formal charges. But right now, I'm going to tell you this one is not going to be our winner because of that -2. So for carbon, 4 valence electrons, 0 dots, 4 lines, so carbon's a 0. For this oxygen, 6 valence electrons minus 2 dots and 3 lines, this is a +1. Okay, middle guy. 5 valence electrons minus 4 dots and 2 lines, I got a -1. Carbon is going to be 4 valence electrons minus 0 dots and 4 lines, going to be a 0. Oxygen is going to be 6 valence electrons minus 4 dots and 2 lines, it's going to be a 0. That one's way better. I've got 2 zeros and a -1 compared to a -2, a 0, and a +1. So I'm like, again, I'm just going to ignore him immediately. But we don't know that this is necessarily our winner, so let's keep going. So 5 minus 2 dots and 3 lines, 0. Carbon, 4 minus 0 dots and 4 lines, 0. Oxygen, 6 minus 6 dots and 1 line, -1. Well, crap. So I have 2 structures that have a 0 and a 0 and a -1. So in terms of who has the most zeros, well, they have the same number of zeros. But in one, the -1's on the nitrogen, and in the other one, it's on the oxygen. So looking at the second statement here. If there's going to be a negative formal charge, it's going to be on the most electronegative atom. So we need to look at our periodic table and decide who's more electronegative, nitrogen or oxygen. And oxygen it is. So this is our best Lewis structure. Oh, holy crap, this video is long. We're going to go back to one of the pictures that we drew and calculate the formal charges. Okay, we're going to do one because then, whoops, what did I just, no. Oh my gosh, no. Let's change to green. Okay, so the green is going to be the formal charges. So I'm going to calculate the formal charge for all of these. So again, the equation, formal charge is equal to the number of valence electrons minus number of dots plus the number of lines. Okay, so this oxygen there's a floating red thing there that shouldn't be there. This oxygen, 6 valence electrons, because all oxygens have 6 valence electrons, minus 6 dots and 1 line, so I get a negative. Okay. This one, I could recognize it looks exactly the same, or 6 valence electrons minus 6 dots and 1 line, I get a minus. Oxygen, over here, 6 valence electrons minus 4 dots and 2 lines, I get a 0. And carbon, I get 4 valence electrons minus 0 dots and 4 lines, I get a 0. So you might look at this and be like, okay, they're supposed to be zeros. That's what they're supposed to be. But if we go back and look at the structure at the beginning, you see how it has a -2 charge right there? That means it's not possible for all of them to be zeros. So at this point, I have a -1 on one oxygen and a -1 on another oxygen. If we have to have a negative charge, we want to be a -1 to be on the most electronegative element. Well, oxygen is more electronegative than carbon, so that's good. And honestly, since this is a -2, like the charge is a -2, it's so much better to have 2 -1s spread throughout than having one atom that's a -2. Remember how I said if you see a -2 or a +2, you're wrong? So this is the best structure that we've got. Okay, so we're going to keep drawing Lewis structures for the rest of Chapter 8 and all of Chapter 9. So good news is there's going to be lots of practice.